So everyone is of you are able to see the whiteboard, right? 13 people are able to see the whiteboard. Okay, great. Uh, okay, just a second. Yeah. So basically, we learn about this LinkedIn. Sorry.
Binary section philosophy.
Yeah. So we learn about this linked list. Okay, the page is a linked list first, right? So linked
Yeah.
list has some structure. Uh, Before going to graph, let me relate it with the topic which we have covered, so that it would be easy to understand how to solve the problem related to graph, right? So today's session, because graph is a little bit tough, or we can say complex topic in DSA. So we also have another class for for this graph, where we will cover this BFS and DFS. So in today's session, I will mostly cover the basic concept of graph, and I will be solving the most of the question in the upcoming sessions. Okay. So if any one of you have any kind of doubt, please let me know during the class itself. Okay. So first we have learned the linked list, that we have some kind of structure uh, for particular object, where we have this two field. One field is reserved for data, whatever we want to store inside this, like we have array, we have common variables. So where we only care about the values. But in linked list, we have two fields. One is for that data or for the value, and another is for linking that node, or we call it node, right? So linking this node to other node, similar kind of node. So that is the concept of linked list, where we have this data and link. When we move to this doubly linked list, so we have another structure like this, uh, where we have data. So if I'm showing data like this, it doesn't mean that we are storing data in middle field. Like this is the structure where we have three fields. So it may be in any order, but one field is for data, like putting the data of that particular object, and other two are for linking with other nodes. So let's say it may be previous like this and next like this, but the good representation is this, that we have data in between, in the middle one, and we have left or previous right like this, and next node for connecting the this next node. For example, let's say we have the bunch of node like this. So let's create a single linked list. So what we can have a data and a link. This is the link. So this is connected to this, then this connected to this, and this connected to this, and this is connecting to null, right? And we have the head pointer to perform any operation on this linked list. So that is the simple linked list. When we talk about the doubly linked list, so we have double link, like this is the single link. So we have double link. So let's say we have three fields. So this is null. This is null. Okay, and this is the, let's say, tail. We have extra field like this. Okay, so this is tail. You can say this is tail, and this link to this, and this link to this, and this link come here. So now in linked list, if we have single linked list, we can go in this direction, but if we have doubly linked list, so we can go in this direction as well as in this direction. So this is the linear data structure. Now when we can modify it like this, like we have a data, and we have this left, and we have this right. Okay, So similarly here again we have data. So we have left and we have right, and like here we have left and we have right. So till now this singly linked list and then doubly linked list or circular linked list or all these are linear data structure because we are going in a linear fashion. This is known as hierarchical data structure, or we can say tree. So if we have only two fields apart from this data, if we have two extra fields, then it is known as binary tree, right? So it let me scroll down so that you can have a fresh page. So here, so if we have a structure like this, so if we have two fields, so it is known as binary tree. But let's say if we have n fields or n child, so it called as n-ary trees. So let's say we have data here, and then we have this is child 1 C1, this is child 2, this is child 3, and dot 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 child n. Okay, so we can also have this kind of data, but like in data structure we don't need to worry about this because we only take care of we only like use binary tree where we have one data node and two like two pointer. First one is pointing to left and another is pointing to right. Okay, so we have learned these things and we also solved some problem related to this, right? And we cannot go upward to this parent. If we are here, let's say if we are here, we cannot go from here to here without any like special operation. Let's say if we have another field, we can also have another field with parent. So let's say if we are solving some problem, we can also utilize this field. We can add this field parent and we can come back to parent. But as I already explained that most of the problem of binary tree or binary search tree can be solved through the recursion. That means you don't need to worry about coming back to the parent because recursion itself, when we complete the execution here, the control automatically come to its parents. And then if the like all the operations completed here, then the this control will automatically come to the parent. So we don't need this parent pointer, but in some problem we need that. So if you have practiced some question or related to this BST or this binary tree, you must have seen that like in some problem we need to check parent as well. So if you are facing any like any problem where you need a parent data as well, so you can use an extra pointer with parent. So it like it has one data field and three pointer, but it is still a binary tree. Why? Because these are the field to linking other node as a child. It is a special node for pointing to the parent. So it is still a binary tree. Now let's come to the graph. So graph is basically when we have a connection like this, we have node. So for simplicity, I am this node is defined like this. And if they are connected with like this in any fashion, let's say like this or like this or this. So this is known as graph. So it may be like, let's say if I writing like this. Okay, so this is also a graph, and we can say this is also a tree if we design like this, this. This structure is similar to this structure, so we can also say that tree also is a graph. But the definition of graph is like this, like any node connected with any other node. So we can have connection like this, we can have connection like this, we can have connection like this. So this is known as graph. Okay, so like most of the problem will be similar to tree itself, but here we have multiple links. Okay, any doubt till here?
Yeah, good. So like in trees, like we usually have one node has two links, basically binary tree. Here, like there is no limitation, like any node connected to any node and any number of links. Kind of
Yeah. So yeah, great. So basically any node connect with any other node. So it may have like n pointers. So for representing this, we are not going to use that complex structure like this. Okay, so let's say if I am going to go with this, so let's say this is the node A. So for A, here we can have the data, let's say 10. We can say 10, and then we can have these number of pointers where let's say if, it is connected to B, right? So we can say B is connected. Let's say this is C. C is not connected, so we can say null. Let's say this is D. D is connected, so we can say D is connected, or we can also use 0, 1 as well. And it is not connected to, let's say, E. So E, this will be null, and it is connected to, let's say, F. So F is there. So either we can use 0, 1. That is one representation through the same structure as we use in linked list or in W linked list or in tree. But the better way is to draw a matrix like this. Okay, here what we have A, B, C, D, or E, and F. Sorry. Okay, just a second. F. Okay, and here also we have A, B, C, D, E, and F. And here, if like A will connected with A, so we can say 1. A with connected with B or not, so we can say S. A is it's connected, so we can say 1. A is connected with C, no, so we can say 0. A is connected with D, yes, A is connected with D, we can say 1. And A is connected with E, A is connected, no, we can say 0. A is connected with F, no, so we can say G, yeah, it is connected, we can say 1. So here, like we haven't defined any direction here. So if A is connected with B, definitely B is also connected with A. So we can go like this. But let's say we have a pointer like this, then A is connected to D, but D is not connected to A. But we are not going to use this. But in special cases, we also like see these kind of problems. Okay, so where you will see, so through this matrix, we can get the fully graph. Yeah, someone is asking something.
So in this example, A is connected to D, but D is not connected to A.
Yeah, if we are using this annotation.
I mean, like if you do the direction, then
yeah, if it is a directed graph, then we will have this direction. Like in linked list, we have singly linked list and doubly linked list. But in graph, we generally show connection like this, that if A is connected by B and B is connected, so B is connected by A. So basically, graph problem are like used for like problem like constructing a road. Let's say if we have 5 cities, A, B, C, D, E, right? So we will see problem like this, that okay, I am a engineer and I just want to connect all these roads with the minimum number of minimum distance, or let's say minimum cost, or let's say minimum materials and all. So what we need to do, I need to connect. So if I am connecting A with B, that means definitely I have connected B with A, right? So in graph, generally, yeah. Suresh, are you saying something?
I mean, like, is direction is not considered that much serious, you mean to say, basically. So
like you may see some problem related to this. So let's say if like if you have a like question related to direction, so I am explaining this, but in the problem you won't see this directed graph much.
Understood.
Like
Got
okay
it.
Because this problem would be like we want to find the shortest route from A to D, right? And let's say we want to connect all the cities. This kind of problem you will see. So you don't need to worry about this. But let's say if you, I will not explain this today. And if you see the problem, so you will say that okay, I don't know about this. So that's why I explain it. In some cases, you may see that there is a directed graph. That means and you will see here. Let's say if you going from A to B, the cost is 10, and if you are going from B to A, the cost is different, let's say 12. In that case, we need a direction. If we are going from A to B, then the cost is 10. If we are going from B to A, then the cost is 12. In that case, we need a direction as well. But let's say if both the costs are same, then we don't need these directions and all. Okay. So in most of the problem, you don't need to worry about the directions. But let's say if you have a direction, then you can utilize that as well. Okay. Yeah. So you can use either this way. So that is not a, I must say that is not a good way. Like you need to create a node for every this structure for every node, and you need to update this every time. Let's say if you are making some connections or deleting some connection, then you need to make all these changes with all these things. You can do that in the routing algorithm we use that, but I suggest that you should solve the problem through this matrix only, because you don't need to solve that much complex problem, right? This routing a mechanism, or let's say some this IP address related things. You don't need to solve that in the DSA part. So the best way is to utilize this kind of representation. Okay. So we can so like this. So let's say if this is C and this is C, so it will be 1. Let's say this is F. If we have 1, that means C is connected with F, and if this F and C, let's say C is coming here, F is coming here, it is 0. That means it is a directed graph where C is connected to F, but F is not connected to C. Okay. That is in case of this arrow, right? But you want to see, so if we have 1 here, so definitely 1 would be here. So in many cases, you don't need to worry about the whole matrix. You can either go with the upper triangle or lower triangle. Okay. You can also go with like this. Okay.
Understood.
Okay. So we can go with this or we can go with this, but I suggest you should go with this. Okay. Now you
I had a question.
Yeah.
So problems like, for example, if you're given a location in with 2 variables, say 5,7, something like that, and then that's kind of like a grid, and you have to, for example, say place a locker, and then there are certain conditions which say that the locker should be away from the existing locker. It's kind of like street cross and then one of the locker is here, other locker is there, other locker is there, and then you are given a new locker with certain set of conditions that you have to place that locker this much distance away from any of the existing locker. Those kind of questions could be solved with similar graphs, or is it some certain separate technique?
Okay. So this is just a representation of graph that which is connected. Now you are talking about this cost that, which associated with this. So like if you have the coordinate for this, let's say x and y, x1 and y1, and we have x2 and y2, right? So you know that in the mathematics we can find the distance. So we can say under root x1 minus x2 whole square plus y1 minus y2 whole square, right? This is the formula.
Distance between the 2 coordinates. That's right. Yes.
Yeah. Okay. So you will get the distance, direct distance from B to F, right? So if you have a coordinate, I'm not saying that you will get a question and you just need to solve that. You will get some question in different manner, but you need to convert it as you want a distance from, let's say the locker. Let's say locker is at let's say x. Okay. So you want that. Okay. This is at coordinate, let's say some x and y n. Okay. Now if you want to find the distance from here, so what you can do, you can convert this graph into by this coordinate. You can find the distance between this. So let's say this is d1, this is d2, this is d3, this is d4, right? So now the graph is converted to a basic graph with given the cost. Now what you can do, you can apply a if you want a minimum distance, so you can apply a algorithm for finding the minimum distance in a graph, right? So you can solve problem accordingly. That's why I already explained in the starting that graph is a very big topic, and generally we skip this topic during our study in the colleges. So we also have other sessions related to the graph problem. So today I am explaining all the like basics of graph, so that how we can approach to the problem, right? So as I explained that what I will do, I will first convert this coordinate into a distance, and then I can apply appropriate algorithm for finding the distance. Like we have two distances from B to X. One is going through like this, and another is going through like this, right? Now, if I just need to find the distance, then I can go with the this path or this path, and I will get two different this distances. Now, if I want a minimum one, either I can go with this like minimum of these two, but we cannot go like this in graph, because let me draw another graph, a complex one. Let's say I want a distance from here till here, okay? And this is connected like this. Let's say it's connected like this, or it may have more edges. So now from here to here, we have many paths. Like one path is like this. This is one path. This is the second path. This is the third path, and so on. So we have n number of paths. So we cannot go like this, that okay, find all the possible paths and then find the minimum one. Okay. So we should have some algorithm that okay, from here we can either go here, here, here. Like, so we should choose any one of them. Then let's say if I am choosing this one, so I should choose either I should go here, I should go here, I should go here, I should go here. So these are the different algorithms which we learn, right? So from here we can go here and so on. So this problem can be solved only when you are good with the basic concept of this graph. So it may like you will see a graph like this, that okay, oh sorry, yeah, so you will get graph like this. So if I'm talking about this ABC like this and ABC like this, okay, so when I talk about 0 and 1, so that was a connection only. But in that case, let's say we can say that A to A, the cost is 0. A to B, the cost is, let's say 10, or distance is 10, so we can say 10. So the same representation can be differ according to the requirement. So here this 10 means if we have a value with greater than 0, that means it is connected, and the distance between A and B is 10. Okay. Any doubt?
Yeah, clear actually. Yeah, go ahead.
Okay, so this is the like way of representing the complex thing in a very simple manner. Like we have a 2D array, and we already solved many problem on like array and 2D array, right? So if we are good to solve problem in 2D array, we can also solve some problem in graph as well. Definitely we need to put more effort, and we need to like take more like things in consideration. But yeah, definitely we can solve the problem using array itself. All the method, all the approaches which are useful in array, we can use that here as well, because we have high array. But in graph we also need, like as been I explained the linked list tree, everything. So we cannot go backward, right? In tree, in linked list, we don't need to worry about the things which we have explored. Okay, just a second. One question in the chat. Can we take a specific question in end of the class and continue with the today's agenda? Okay, we'll see. First, let me complete the basics, and definitely we will solve at least 5 to 10 problem in the next session, next this BFS DFS sessions. So don't worry about the question, but okay, yeah. So what I was explaining, I forgot. Okay, so apart from this 2D matrix, as we are not like in the other data structure, we are not going backward. For like, let's say let me give you an example. Let's say we are here, and we have, let's say, n cities like this, and we want to visit all the cities. So we visit this city and we come to this city and we come to this city. So we were thinking that, okay, I have covered this city, then this city and this city. So I am coming it twice, right? But I should not come twice. So I need to remember these things. But the let's say the graph is having, let's say, 1 million or 1,000 cities. Okay, so let's say 1K nodes. So we cannot remember that, okay, whether I visited here or not. So we also need to take another 2D matrix, same 2D matrix with visited. So it may be a Boolean value 0 or 1. 0 means we haven't visited it. 1 means we have visited it. So if we are using this matrix, so that we can find, okay, from here we have 3 options, right? We can go here, we can go here, or we can go here. Okay, we have 3 options. Now we can check if we are going here. We are going here first. If we are going here first time, then we can go here. But this node is already visited. Like we come here from here. So this node is already visited and we mark it as visited, or we can say with 1. So we are not going to go back here. Let's say if I want to find the cost from A to B, let's say, right, or A to C. Okay, so the what we can do, the cost from A to B is 10, and let's say B to A is also 10, because this is not a directed graph, but I'm defining a like with 2 edges. So let's say if I am going from A to B and B to A to B, B to A to B, we are keep on moving here cell, so the cost would be infinite. We never reach here, or let's say after 10 round we reach here. So that answer is not a valid answer, right? So for that point, we need to take another matrix. This is the graph matrix on which we take all the data and perform all the algorithm. And we will also use this 2D matrix with visited. We can name it anything, like so we can say visit or visited or anything, whatever you want. But we should have a Boolean value for all the nodes, whether we have visited. Sometimes we need to visit 2 times, so we can also make a counter here, 1 0 1 2. So we can do that as well. Okay. So for solving problem of graph, we should use this matrix and apply appropriate algorithms. Apart from this, we should take like keep track of this matrix, this visited one, and we are going to define many functions. Like one function is calling another and so on. So we should create a like this these 2 matrices in the parent function, and we should pass this matrix in the like all the function calls, so that let's say if this matrix is updated in between and we are coming back, so the same updated matrix also like come back to the parent parent function. So for solving the problem, we have this. We are, after this we can apply many algorithm on 2D arrays, and we should have this visited one, so that we can say that, okay, whether we have visited this node or not. Okay, any doubt till here?
Yeah, good.
Okay, so that would be a like main agenda when we are solving the problem. Many many of us make this the mistake that we know the algorithm, we know how to solve the problem, and we are applying the same algorithm on this matrix, but we forget to take this visited, or we take this visited as well, but we forget to update this thing, so you won't get a correct output, right? So you will see, like many times you will see this sometime you will see this infinite loop, you won't see any output. It's taking TLE, like time limit exceed. So it may be due to this, because you are not updating this correctly, and you are visiting the same node again and again, so it is keep on like going in the loops. So like tree, we also use recursion here in many places. Okay, so you like in recursion we need 3 conditions. Just scroll down the whiteboard. We have 3 conditions. First one is this edge case. You see edge case where we should stop, like in the case of tree, we should return from the, if the root this node is null, so we should return. That is the edge case. Second one, the actual logic. That means what we are doing in this function. And third one is this recursion call, how we are calling the function recursively, right? Similarly, here in graph, we have this matrix. So we have a budgeted matrix. Okay, we have a matrix and we have a budgeted matrix. So here we should know that whenever we are getting an output, we should break, so that condition would remain same. The most important thing is we should update this correctly. When, let's say, if we are not updating it and any function, or we are missing something, so we'll definitely see a different output. And it would be very tough to investigate like the code, that okay, what is the problem. So it would be easy to write the code from scratch. So sometime if you are solving a problem of graph, and let's say if you are investing let's say 1 hour, and you are not able to solve the problem, you are writing the correct algorithm, you are writing the correct logic, writing a correct code, but still if you are not able to solve the problem, you are not getting the correct output. So I will suggest, don't try to correct your code, just copy paste your code somewhere else and write your code from scratch, because you will not get where you are missing this the things. So what you can do, you can write your code from scratch, so that you can find that mistake, and then when you submit all the test cases, then you can compare with your previous code, that okay, what was the issue, so that in the future when you face the same problem during your interview or during anywhere, so you will have the idea that okay, if I'm getting this kind of problem, that may be the problem. So I'm remember, during your practice, don't start from scratch. Let's say if you are not able to solve the problem, the best way is delete everything and start from scratch. But before that, you should copy that old code which is not working, and after starting from scratch, you should also compare your mistakes, so that when you are facing the same mistake, you are doing the same mistake in the let's say in the interview or somewhere, so you can resolve that. You will get an idea that okay, we are getting this kind of issue, that means I may miss something in this function and all. So that would be a good analysis for yourself, because when you are working for an organization or when you are giving an interview, then it is quite difficult to debug some other code and find the bug, and that will come through this. And you will see most of you will not able to solve any graph problem in a single run. Even when I used to write a code for a graph or tree, so many time I got a either compilation error or sometime runtime error, or sometime I'll get because we use here pointers, so we get null pointer exception, and sometimes we get a infinite loop, so we get TLE. So if you practice more and if you investigate your code, then it would be good for you. Okay, so I think I covered most of the basic thing. Let me check if anything is missing. Yeah, so I have explained this matrix representation and this linked list representation, and okay, I have covered almost all the things. Yeah. Okay, great. Great. Now, today I'm not going to write any code, so don't worry, because this topic is quite difficult. So I am giving you some example, and I'll try to solve some problem with you. Okay, we are not going to write any code. We will start from DFS and BFS. So why we start from DFS and BFS? Because you already solved these problem in trees. Like we have done a label order traversal like in tree. So let me explain DFS and BFS first. And BFS. So DFS means depth first search, and BFS means breadth first search. So let's say we have graph like this. Okay. like this. Okay, so just think like this, but we don't have any depth and breadth in the graph, but just assume like this. Okay, so when we are talking about, and let's say it is not connected with let's say this one. Okay, yeah, this is not or let's say, let me do like this, this and this. Okay, like this. Okay, so we are here. So the first thing, let's start with DFS. DFS means we will go into depth first. So let's say if we are here, we can choose anything, like either I can go here, I can go here, or I can go here. Let's say I am choosing this path, or let's say this path. Okay, so I will go here. I perform the operation here. I perform the operation here, whatever operation I want to perform or whatever problem I'm solving. I just check for here, then this is connected to this, 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 but this is visited. That means I have covered one depth, full one depth. I come back here, right? So after this, because we are using recursion, so I will come back and then I will select another path. So I cannot go with this path because this node is already covered, right? This is already visited. Now I can choose another path. So let's say I'm choosing this path, and after this I again have two paths. So I have to choose any one path because we are going to the depth. So here I can choose either this one or this one. So let's say I'm choosing this one. So I will go there. This is visited, and I will come here. This is visited. Again, we don't have anything. We have null. So we will return back because this is the recursion. So eventually we will return, and now we have another path. So we will go here. We will visit this. We will visit this, and at the end we can return back here. So this is the depth first set. Like we have went to the depth of one path, and then we are picking another path in every node. So depth means is not mean that you are let's say if we have a node like this, after completing this you cannot pick this one because this is in between this path. So after completing this you should return back in the same order because recursion return in the same order. So you will return here and you have to discover this path, right? So eventually program itself discover this path if you are using this DFS. Okay, now what is BFS? BFS means breadth first search. So I will select the node which is reachable to me. So what we can see, we can connect this one, then this one, then this one in the first order, in the first pass or first run. So we will cover this one like this, this. So this is from here, this is the source. So we can cover all the nodes which is in a unit distance. So that's the distance is 1. Okay, or we can say single edge. Then we can cover all the distances with 2, all the node with distance 2. So we can say we can cover this one, we can cover this one, we can cover this one and this one. Let me write like this so that you can. So you can see all these nodes are with the distance of 2. Then we can cover this one, this one, this one, this one. Okay, so this is cover from here. As you can see, if you are not using a visited one and you are using a BFS, so you will cover this node from here as well and from here as well. That's why we need a visited. So we should not visit this 2 times because it is in the distance of 3, 1, 2, and 3. Okay, 1, 2, 3. But here the problem is we are also visiting it from here as well as from here. So we should also take care of that. So this is the BFS and DFS. So let me show the same thing through tree so that you will get a better idea. So let's say we have a tree like this. Okay, let me use the numbers. Just to scroll down. Let's say 1, 2, 3, 4, 5, 6, 7, let's say 8, and let's say 9. Now, if I am going with the depth first search, so what I will do, I will go with the left and then right. Okay, so I will follow the same order. So depth first search will go like this. So it will print, let's say depth first search. So it will print like 1, 2, 4, 9. then it will come back and then go for right. So it will print 5 and come back. It will go for 3, 6, 3, 6. Then it will come back to 3, 7, 8. 7, 8. It would be a depth first search. And if we are going with breadth first search, so we are going with the 0 level, that means 1. Then first level, that means 2 and 3. Then we are going with 4, 6, 7. 4, 5, 6, 7, and then 9 and 8. 9 and 8. So this is the breadth first search. Like we are going by level. So we have solved both these problem in the tree itself. So we have solved problem related to yeah. We have solved this problem for this tree traversal, right? Pre-order, post-order, and so we are using this DFS. And when we are going with the this label order traversal, so we were using what? We were using this BFS. So here, can anyone tell me that if we are using this DFS, which data structure we are going to use?
The pre-order traversal, right? Basically,
yeah,
for binary tree.
Yeah. So if we are going with pre-order, post-order, or any order, basically we are going with DFS because we are going till the depth, and then we are performing more operation. So can you tell me the which data structure we are going to use in DFS?
Trees, right?
Okay. Sorry?
Trees, right?
Tree or what you are saying? Tree or stack?
Trees.
I think
Tree.
stack, because push and pop.
Yeah, we are using stack. So we don't need to use stack actually because we are calling it recursively. So that recursion itself use a stack, right?
Yeah, that's right.
So you're saying default implementation of recursion is stack.
Yeah,
right?
yeah.
Okay.
Yeah. And what should be the data structure used in BFS? We have solved this problem, right?
That is queue actually.
Yeah. So basically we use queue. So the for DFS, eventually we are by default we are using stack, and for BFS we are going to use queues. So you need to when you are solving some problem, so the same graph can be visited through DFS as well as BFS. So whenever you are solving the problem, first when you decide that okay you are going to use BFS or DFS for this particular problem, so when you are deciding it, then you are going to decide the data structure as well. So if you are using with the BFS, so you have to use queue. That means your 50% problem is already solved. You know which data structure you need to use for solving this problem, right? Actually this graph is quite complex. That's why I'm explaining it in a breaks. Okay, so first I explain about the graph. Now I am explaining how you can think that which data structure should I use. So 99% of cases, if you are solving a problem through BFS, then definitely you are going to use this queue 99% of cases. Okay, and if you are using this DFS, so in tree we are using this stack by default, but in graph you may use this stack through the recursion. But in some cases you need to define your own stack, right? Here as well you may use single queue, or you have to define multiple queues, or let's say 2 queues or 3 queues. Similarly here, like most of the problem will be solved through queue itself. Here most of the problem will be solved through stack recursion itself. But in some cases you need to define a stack separately, because stack is doing a some fixed kind of things. But let's say if you need some modification during this calculation, then you should define your own stack. Okay, so let's start with the some problem related to this graph, or let's say this DFS BFS. So everyone know about the snake ladder game, like, or let's say chess. Okay, so let's say we have this chessboard. So I'm drawing a small chessboard. Okay, I'm not drawing this actual chessboard. I'm just giving a let's say we have this matrix, and we are here, and I just want to know whether I can reach here or not. Okay, like if you played a computer generated chess, so when you click on particular things, so you will that computer will show you the path. So let's say if you are, if we can move it in this direction, so you will see this direction is highlighted. So how we can calculate that? So what we know that, okay, how this will, how much step this can run. Okay, so let's say if I want to jump it one step up, in the straight direction, like he can jump like this, he can jump like this, and he can skip one step, so he can jump like 2 steps. Okay, so can we reach from here to here? What we can do, we can go here or we can go here. Like again, we can, from here we cannot go here because we don't have another step. We can either go here, right, and from here we can go here. So we are not able to reach here, but wait, can we have any other option? I think no. Yeah, so we cannot reach here. Like in this case, that like it is skipping one, it is taking 2 steps in a single run. So it can move here, and so this is the DFS. DFS means we are going here, then here, then here, then here. That means we have covered all the things. So in this path, we are not able to cover. So then we can go with this path. We are not, but this is already visited. So this is the BFS, DFS. And if we are going with DFS, so we should go in the both paths simultaneously. So we can put a queue and we can go here as well as here. From here, we can go here. And from here, we don't need to go here because this is already visited. We can say we cannot reach here because we don't have any other position. We cannot go anything anywhere here. We can jump back here, but this is already visited, and so on. So did you guys understand like what I am trying to explain here, or should I explain it again? Anyone?
Got it.
Sorry.
Yeah, got it.
Okay, so basically, you can if you want to solve problem related to graph. So what you can do, you can solve the problem of chess. So let's say we have n numbers of n number of operations in the chess, right? Like some can move in single direction, some can move in diagonal, some can move like this. So for every possible way, you can solve a problem for using this DFS and BFS. That okay, how we can go like this, how king is where king what are the possibilities of king, what are the possibility of queen, and all other members of this chess. So what you can do after this class, if you want to solve some problem, what the best way is you can pick any game. It may be a snake ladder game where we have this kind of things. Something we have some ladder like this. We have some snake like, let's say like this, and you are going like this, and if you found this leader, so you can go directly here. And if you come here and you can directly come back here. So what you can do, you have a dice. So dice may have 0, not 0, 1, 2, 3, 4, and 5, and 6. What you can do, you can use a queue. If we are getting 1, what will happen? If we are getting 2, what will happen? And so on. And you can solve the problem related to this game or related to this game. Very good. These like you can solve through this DFS and BFS only. But definitely we will solve these problems in the class itself. But if you want to solve, you can solve this problem. Let's say if you are not able to understand how we can solve this, you can go for a code available online, and you can take help, so that if you are taking a help and solving one problem, you can solve other let's say n problem with the help of this code. So you can check that, and you can solve those problems. Any doubt till here? Anyone?
Yeah, good, Shalik.
So if I ask you to solve let's say 10 problems, So can how many of you can solve those 10 problems related to these operations? Like, are you able to solve like at least one or two problem on graph?
Yeah, so if you have some problems, kind of list based on this explanation, like we can give it a try before the class. So,
Mhm. Sorry, can you repeat what like your voice is quite slow?
like if you have some questions in your mind, like state code number, something like that, so give to us, like look at it and try to solve it.
Yeah. So what you can do, you can go to like you can open your browser and you can type graph related question related to chess, related to this game, or simply a graph related question. So why I'm like asking about these related to these two games, because this is quite related with only DFS and BFS,
Yeah,
right?
sure.
And you can also solve problem like this. Let's say if you can say the like standard problem is traveling salesman problem. You can also solve that also, but let's say don't go with that complex problem. Just solve the problem that okay, you have n cities, okay, and you have the cost associated with each cities, and you need to visit all the cities with minimum number of let's say minimum cost. You can go with this, so you can solve the minimum spanning trees problem and so on. But I'll suggest you should solve this problem that will be like that you can solve through this DFS BFS, and after that if you have time then you can go with this complex problem. Okay.
Yeah, sure.
Like what you can say that you have a chessboard, or let's say a board, and you are here and you have some rule, so you can find that question on the internet, or you can define your rule by your own also, as well. You can like create your own game, like a small game, not a game, you can say a piece of game, the piece of a game. So what you can say that okay, I am here and I just want to go here, and I have some a set of rules that I cannot go in any straight, I can only go in the diagonal, and after diagonal I should after like in one time I can go diagonally, like in this box, and then I should go for two times for this either here and here, and then I can again I will go in this diagonal. So like if you played any game, so there are some rules in that game, right?
Yes.
That rules are defined by the this developers. So you can also create your own game. You can define your own rules, and you can perform that operation. That okay, if I am here and I want to reach here, let's see whether with this rule if I am able to reach here or not. So you can print 0 or 1. If you are able to reach here, you can print 0. Oh, sorry, 1. If you are not able to reach here, you can print 0. That would be a one question. Now let's make it more difficult. So what with the minimum number of steps through which I can move here, from here to here. Let's say I am going like this. So there are n number of way to reaching from here to here. Now I need a minimum number of steps, minimum steps. How I can do this? So either you can go with BFS or DFS. What should be the better way? That you need to think. So if you are going with the DFS, definitely you will pick a one route and complete that route. So you need to find all the routes, and then you need to find the minimum one. So that won't a good like good approach. So what you can do, you can go with the BFS here, and you can solve this problem. Okay. So you can solve these kind of problems, and let me see, the next session would be next session, or you can enroll to this like road to fang for software engineers, and here you will get this these problems like find the town judge and all. So you will get that problem, and you will also get this lead code link here as well. Okay. And apart from this, you can complete your profile so that like if you are like uh, if someone is looking for hiring, they can look the profile and directly reach out to you. Okay. So I think that's it from my end for the session. If any one of you want to know about the like paid courses or paid services, then you can stay. Otherwise, if you don't have any doubt, then you can drop. And we will meet on just a second. Let me check. The next session is graph, heap. So we have DFS and BFS after heap and dynamic programming. So should I go with this heap and dynamic programming, or BFS, DFS first, and then I should go with in these topics? Any
Take more classes on the graph actually, like one class on the BFS problems and one class on the DFS problems, like that, because yeah, these kind of more complex.
Okay, fine. So I'll discuss with Rahul and like let you know about the next class. But like I believe I explained about this graph so that you can practice some question on graph, right?
Yeah, sure. I already looked into it actually, so going through at the depth